Today we're actually going to round things off a little bit with LeChatelier's principle. We're going to so warm things up. I'll let you think about this problem for a little bit. Read what it says on the slide. We'll talk about it. So we have our very simple equilibrium here between carbon dioxide gas and carbon dioxide aqueous. This should be something you're kind of familiar with, actually, because you see it frequently in daily life. We want to know about these two stresses we have, an increase in temperature and a decrease in the concentration of the gaseous carbon dioxide. Given the delta H value we have here, and that it's less than 0, citation below, we can say this is an exothermic reaction, so that heat is a product. And since heat is a product, an increase in temperature should cause a shift away from that. So we're going to shift toward reactants, or a shift left. And a decrease in the carbon dioxide gas concentration, again, this is going to bring us towards the left. It's a reactant, there's going to be less reactant, so in your equilibrium, the forward reaction slows down, the reverse reaction doesn't initially. It slows down to catch up, but then you're going to build up a little bit more reactants. So again, we're going to get a leftward shift towards. And I picked this example for a very specific reason. Both of these changes would be exactly what happens if you take a can of soda out of the refrigerator and let it come to room temperature and then open it very suddenly. Those two stresses, you increase temperature, and when you open up the soda container, all the gaseous carbon dioxide above the soda rushes out of the container, and so you get a lot more gas being created very suddenly. But this actually kind of gets us towards a different stress, something we haven't seen before. It's also true that when you have a soda can that's sealed, the contents are under pressure. In fact, it's kind of hard to decrease the concentration of carbon dioxide unless you are changing the pressure. And so to get things started with today, I wanted to show you one more video. I have another example of an equilibrium process. No words, so just watch it. The video is actually from, I'll link it in the description. I found it's in German. I went and translated all the words to make sure all of them are at least appropriate and topical to the content. But again, just watch and take some notes based on what you see. I believe that means increased pressure. Oh, that's interesting. Oh, we'll talk about. Oh, I like that. There's a good one. So I'm going to say I noticed 4 things. Okay, 5 things. We're going to start off with, clearly there's a brown gas. When we push, we see 2 things. First, it gets darker. Then, at some later time, it gets lighter. And then when there's a pull on the plunger, it gets lighter. And then it gets darker. I want you to take a second, and I want you to rewind in this. Go watch this again, or go click the link so you can watch it yourself. I want you to make sure that you can see all 4 of those changes. That when there's a push, it initially gets darker, and then it gets lighter. And then when there's a pull, it initially gets lighter, and then it gets a little darker. That there should be 2 different changes there. If you don't see them, maybe I'll find another link of someone else doing the same video that might be a little easier to see. I'll include that one too. This is such an interesting equilibrium because you can actually see all four changes pretty clearly. And if you can't catch on this one, I think I have a better example I'll link. I just didn't like the other example because they kind of did that thing, where they like explain everything and it ruins everything. And you'll see what I mean. But I want to step in and talk about that. Before we talk about the NO2, though, I want to talk about an equilibrium that we're a little bit more accustomed to talking about, this ammonia equilibrium. So suppose we have a closed container at equilibrium. I'm going to draw my closed container. I might need to draw a couple of closed containers, actually. And in our container, we've got some N2s and we've got some H2s. And I'm just going to draw the stoichiometric amounts, and we've got some NH3s. And, KMT is at play. All these gases are bouncing around, running around all each other, bouncing off the walls. How does the amount of pressure a gas exerts relate to the amount of gas? We know this one. We know from our relationships that there's a direct relationship. And in a direct relationship, N over P equals N over P. That's Dalton's law of partial pressures. So I know that. If this is a situation where all those particles are in there and they're constantly reacting, well, if we were to run the reaction like once, run the forward reaction once, or the reverse reaction once, let's say for this box we run the forward reaction, and in that case, one of the N2s and three of the H2s would turn into two NH3s, and then we'd have the same two NH3s that we had before. And then in this other one, what we should have here is the same N2 and H2s that we had before, and then we would actually create one more N2 and three more H2s as these two NH3s were to break down. If the forward reaction happens, 4 particles becomes 2. For the reverse reaction to happen, 2 becomes 4. If these two containers had the same volume, it seems pretty clear to me that the container on the right would be the one where there would be a larger pressure, because that container now has 8 particles in it, where the container on the left would only have 4 particles in it. So it seems to me that even though this is at equilibrium and the rates are equal, if there's ever a situation where the rates aren't equal, you could actually create a higher or lower pressure just by running either the forward or reverse reaction. Well, if we wanted to make more pressure, we should actually proceed in reverse, because it creates more moles of gas. I think every time it proceeds to the left, we're going to get pressure as an out product. So I kind of think we should put this, if we're going to put the term pressure, it would be a reactant with the larger number of particles. That the more that reaction happens, the more pressurized the inside container gets. You can see we have a container here, and then we've increased the pressure, and then some sort of change happens. And it looks like this is less crowded. Now the thing to remember is this is a sealed container, so I don't know how it looks less crowded in there unless there's now fewer particles, there's fewer molecules, even though there's the same number of atoms. LeChatelier's principle says when the equilibrium is stressed, it will behave in a way to alleviate the stress. So if the external pressure is increased, here we have 4 gas particles, and here we have 2. So each time the forward reaction runs more than the reverse reaction, we're trading out 4 particles for 2, and that's where this less crowded comes in. So if you increase the pressure in this case, that would yield a shift right. If you decrease the pressure, that would be a shift then left. That's why I like having this pressure term in my equation, because, well, shift away from the thing you increased. If you decrease the pressure, shift towards the decrease. We draw a third container here, or fourth, container here, and if we pulled up the plunger even more, you would expect that some more of these would break down to make more particles, and you'd probably see more N2s and H2s and fewer NH3s. So the equilibrium position is changing to... Let's look at a couple more, because this might make a little bit more sense if we keep looking at this. So what I got here, and I tried to get a good set of frames, is this is our initial condition here. This is our after pushing, and then this is the later. And I don't know how well you can see if there's a difference in color between the top and the bottom. If you can't see it, like I said, I'm going to attach a couple videos that you can go watch where they do this better. But I should explain a little bit about this substance. The brown gas isn't everything that's in the container. If you were to try and draw a Lewis structure for NO2, and you counted up how many valence electrons you should have, you get an odd number. It actually adds up to 17 electrons. And because of that, NO2, well, it's got a lot of properties. It's poisonous, but also it likes to pair up. It's kind of like halogens, where it has an odd number of electrons, and it will pair up to alleviate that odd number electron. And so N2O4 is this so-called dimer. And so they pair up. But what happens is, in your container, each time that happens, and this has 2 molecules, so we can actually play around with the pressure, and by playing around with the pressure, you can observe a change in the makeup, in the equilibrium. Now, the very interesting thing about this is that this substance is brown, and this substance is colorless. So if we increase the pressure, what we should see is we should see a shift to the right. And so it should get more colorless, or I guess lighter, if you want to say that. And if we want to decrease the pressure, what you should see is it should get more brown. And that is what you see, but if you remember correctly, if we go back to our initial set of observations, if you push, it gets darker and then it gets lighter, and if you pull, it gets lighter and then it gets darker. So it sounds like these two here are your responses, and then these two are your stresses. And that's why I like seeing this, because you can actually see the stress happen. The reason you see it get darker before it gets lighter, looking at this, when you increase the pressure, yeah, the shift is that it turns more colorless, but initially there's actually something that happens on a much quicker time scale. This is a gas. Boyle's law dictates that as you increase pressure, you decrease volume. And remember that concentration of NO2 is measured in moles per liter. So if volume decreases, NO2 concentration increases. And then the response would be to make less NO2. Now there's a really like foundational caveat with this, in that they both increase in concentration, but we're not going to worry about that. How I want you to think about this is what we talked about in the previous slide, where I would add a term pressure to the side of the reaction, the reactants in this case, where there are more gas particles present. And so it should make sense that if you increase pressure, shifts to the right. If you decrease pressure, shifts to the left. And that shift is the second response. It's the second thing you see, not the first thing you see. That's the most important part. And so just a couple more problems, 2 more problems to look at to wrap our mind around this, because you can also see this show up in problems where it's not a question of pressure changing, it's a question of volume changing, and then you have to think in Boyle's law. And so I forgot there needs to be a colon here, not a period. Colon, I said colon. If the volume of the container is changed from 500 milliliters to 5 liters, how should the equilibrium shift? Well, you've been given 2 units here, so we should probably square that away. The 500 milliliters is 0.5 liters. So what happens is the stress is that volume increased. Well, what does that do for your equilibrium? There's a couple ways to think about it. I prefer to rewrite that as what happens to the pressure. And we know that P1V1 equals P2V2. So if V2 is greater than V1, we know that P2 is going to be less than P1, so the pressure decreased. Now in this case, I see 2 particles of gas in our reactants and 5 particles of gas in our products, so we're going to add pressure as a product in this case. So if the stress is that the pressure decreases, the response is that we're going to try to, the equilibrium will behave in a way that increases the pressure, so that would be a shift right in this case. And that should be consistent logically with what we were talking about before. If the volume suddenly gets bigger, to fill that void, you need more particles of gas. I'm not saying more gas enters the container. I'm saying N2O5s break down to make more particles of O2s and NO2s than you had particles of N2O5s. And that equilibrium shift is that more N2O5s break down than O2s and NO2s come together, until such a time that equilibrium reestablishes. It's all that same idea over and over again. Last thing I want to talk about is catalysts, because that's the other way we've talked about to change the reaction rate, other than surface area, but if you're at equilibrium, that actually kind of balances itself out. Catalysts would be the last part. Now we have seen, I'm just going to draw an exothermic reaction really quick. We've seen this, and we know that this is a reaction proceeding, and this is energy, and if this was a catalyst, we would draw this dotted line, and that this is our alternate pathway. It's literally a different line, and it has a lower activation energy. Interestingly, if you have a catalyst in your equilibrium system, what happens is both the activation energies get lower. I mean, there is a forward and a reverse reaction, but in both cases, instead of being that high, it's now that high. Instead of being that high, it's now that high. And what's very interesting about this is that since both get decreased, what you end up seeing is that both reactions speed up, but unlike the temperature shifts, both reactions speed up equally. And so if they're both getting faster equally, there won't be a shift, there won't be a change due to collisions in any sort of amounts of reactants or products. So if both reactions speed up equally, no shift in position. So you have your, say it's a 2-to-1 ratio of reactants to products, you dump in your catalyst, everything's presumably reacting faster, but you don't see anything because it maintains that 2-to-1 ratio. And so at this point, we've rounded things off with how to shift equilibrium and how that all takes place. So as a brief summary, I should be able to hit the pause button here, and I can't hit your pause button, but I'm suggesting, I want you to take a minute, hit the pause button, and try and figure out how all of these stresses would shift the equilibrium position. Did you pause it? Are you back? Good, you're back. Welcome. Welcome back. I hope you were able to figure that one out. Those 5 out. With an increase of pressure, I see that we have, we got 3 moles of gas and 1 mole of gas, so we're going to shift the equilibrium to the right. With an increase of volume, that's the same as a decrease in pressure, so that should be a shift to the left. With an increase of temperature, well, the wording up here did say it was an exothermic reaction, so that means heat is a product, which means an increase in temperature should shift it to the left. An increase in the amount of H2 should shift it towards the products, and a decrease in the amount of methanol, CH3OH here, should also shift your reaction to the right. Now that I'm thinking about it, I am at the summary a little too soon. There is one more thing I wanted to talk about. And I will hopefully get both settled up if we go all the way back to the do now problem. So we talked about temperature and concentration here, but we can also talk about pressure. Like I said, the soda can, when it's sealed, is at a certain pressure. When you open it, you release the pressure goes down. Well, counting up the particles of gas we have in this equilibrium, we've got 1 particle of gas when you consider the reactants, and there are actually 0 particles of gas, because it's dissolved in solution, when you're looking at your products. There are frequently times when you look at an equilibrium and one or both sides contain 0 gases. And 0 is a number that you can use in this whole process anyway. So to say here, if we decrease the pressure, that should shift the equilibrium towards the reactants. As a final note, there are equilibria where there are an equal number of gases shown in the reactants as there are in the products. A good classic example of that would be, it turns out that hydrogen and iodine gas, and now it does become very important to put your phase labels, can be in equilibrium with this hydrogen iodide particle. This is two particles of gas, and this is also two particles of gas. So for this specific equilibrium, a change in pressure will not affect the equilibrium position because there's no shift that will actually alleviate the stress, so there isn't a shift. There's no response. I hope everything here hasn't been terribly difficult to process. If you do need to go back and watch any of this again, you are of course welcome to. Play it as many times as you need to. And thanks for watching. But there's one more thing I could mention, because I'm sure some of you are wondering. That's great that we talk about how the equilibrium position shifts, but why? Now I'm going to explain this really quickly, because if you are wondering, I will explain it to you. However, if you don't understand what an equilibrium expression is, this is not going to make sense, so you might want to hit the pause button or just take everything that I say with a grain of salt. This is not a Regents topic, but it makes a lot of sense if you follow along. So, the equilibrium expression, K, in this case is going to be equal to the concentration of products over the concentration of the reactants, raised to the power of their coefficients, as these are all assumed to be elementary single-step processes. We're just going to say the rate determining step, and therefore the rate law is what you see there. So this will give us an equilibrium expression of the concentration of N2O4 over the concentration of NO2 squared. And this is very powerful. This explains where that pressure term came from, because you can rewrite each of these concentrations as, well, we know that concentration equals moles over volume. So this would be the number of moles of N2O4 over the volume of N2O4 divided by the moles of NO2 squared over the volume of NO2 squared. But this is a system at equilibrium, and it's one system where you've got all your compounds in one container. So really what I should be saying is that it's not the volume of N2O4 and it's not the volume of NO2, it's just the volume. It's one container, which is super useful if you're going to be doing some algebra here, because now volume is volume is volume, and what you get is that one of the volumes cancels out. One of these V's cancels out one of these V's, and so what you get, and then I'm gonna simplify my fraction because I hate complex fractions. It's volume times the number of moles of N2O4 over the number of moles of NO2 squared. So now it's very simple to see that if the equilibrium constant is to remain a constant, if you increase the volume, you have to decrease the number of moles of N2O4. And if you're going to increase the pressure, you decrease the volume, and you're going to have to increase the number of the moles of N2O4. If volume increases, the number of moles of N2O4 has to go down if K is constant. And because we haven't changed the temperature, K is constant. If volume has gone down, that means pressure has gone up, of course. Then the number of moles of N2O4 to keep K constant has to go up. And it's always going to be the case that the side of the reaction that has more moles of gas will get more V's in the denominator, and therefore it'll actually end up on the opposite side. And it kind of just lays everything out nice and easy, where algebra answers everything. If K stays constant, and it does, this will always make sense, or will at least always be solvable. I hope it makes sense, and thanks for watching.